Hi, so in this video, we'll be talking about the momentum operator and how the momentum operator works on the wave function psi, which is position and time dependent, to give out the momentum of that function as its eigenvalue. So for that, first, let's jump at the year 1924, when Louis de Broglie proposed his PhD thesis, which was a very important discovery for the modern physics. He said, in simpler ways, matters are waves too. They are the matter waves and the waves of probability. And the probability of the function or the particle present at that certain position can be given by the amplitude squared. I have explained about this in the previous video, so please go check it out. And now, let's use his conclusions to further go about the momentum operator. Remember, P, which is the momentum, can also be given by h over lambda. But I can write h as h bar, which is h over 2 pi. So Planck's constant is something 6.6 times 10 to the power negative 34. And h bar over 2 pi has the same order, but it's like 1 point some value times 10 to the power negative 34. That is not important at that point. But let's do 2 pi h bar in terms of h bar over lambda. So 2 pi over lambda is the wave number. So P will be h bar times k. We will be using this. And also I know that E is h times the nu. Nu is the frequency. And this was proposed by Einstein, for which he got the Nobel Prize. So E is h times nu. But I can also write this h as E is 2 pi times h bar times nu. 2 pi times frequency is omega. So E is h bar times omega. This is also one of the important conclusions that we will be using. So let's keep this there and let's try to find out what the momentum operator really is. So let's take our wave function psi now. So my psi, let's decorate psi, x comma t is a plane wave, because this will be very convenient wave function for us to calculate further energy operators and also the Schrodinger's equation, which we will get to very soon. So let's say I have psi wave function k, x comma t as k times e to the power I kx minus omega t. And it's a very common plane wave. Classical electromagnetism also talks about this plane wave a lot, which oscillates in one dimension and has also its complex components. So its amplitude goes complex and real eventually. So now we have psi x comma t as this plane wave. And now, first, since we are calculating momentum, it usually you can just visualize that the momentum is dependent on the position. So let's also take the differentiation of psi, or let's take partial derivative of psi with respect to the position. So let's say partial of psi with x. So since I'm partially deriving the psi with respect to x, this value will go to 0, the exponential term, this will come out, so I will get I times k, let's put this in a nice warm bracket, times k times e to the power the function. This is very trivial differentiation. So I times k, let's also write the whole thing, e to the power I kx minus omega t, which is nothing but ik times psi of x comma t. Now, what I can do is I can substitute the value of k. I know what k is. I know k is p over h bar. So, simply I p over h bar times psi of x comma t. This is the partial derivative of psi with respect to x. So partial of psi is this. Let's also box this because it's important. But I want the momentum. Remember, I just operated the psi by taking its partial with respect to x. that hasn't given me momentum just yet. But it has given me the wave function psi again because of the exponential term. Think about it. So I got the wave function psi, but the eigenvalue of dou psi over dou x is ip over h bar. What I want is just p. So what I can do now is very simple. I just want p, and I want the I term to get cancelled here. So I can multiply this I with negative I, and I can also multiply this whole function with h bar such that the Planck's constant gets cancelled. So what if I say negative I h bar times dou psi by dou t, dou psi by dou x. What will this be? Okay, let's write it down here. Let's be a little bit more systematic this time. So what if I say negative I h bar partial of psi with respect to x? I know what the partial of psi with respect to x is now. I just have to multiply this thing with negative I h bar. I and negative I become 1, and h bar gets cancelled. So here I have p times psi of x comma t. And this is a very important conclusion for us, because this is the momentum operator of the psi function. Remember, what I'm doing is I'm multiplying the function dou psi. I'm taking the partial derivative of psi with respect to x. So suppose I have a wave function psi, then I'm taking this function partial derivative with respect to, if this is my position, then I'm taking the partial derivative. Let's say it's sine function gives me a cosine function, for example. Well, you know the point. I don't have to explain everything here, because I'm expecting you to know the basic formulas or the basic notions of differentiation with respect to x. Let's say let's also draw something very nice here. Let's just calculate a sine wave. It's not like this exactly. It's not normalized, first of all, but just for intuition. Let's say now this gives me this. And now what I'm doing is I am rotating this function by negative I. That is, I'm rotating by 90 degrees clockwise. So when I rotate this function clockwise, what I get is a complex function. So well, I can't draw it here, but if this is my complex realm here in the z direction, then this whole function will get rotated by 90 degrees. And also, I'm just multiplying this whole function, what I get, by h bar, which is a very small number. But this will give me momentum times the same function psi for the calculations that we did just now. So this was the momentum operator. So in the next videos, we'll be talking about the energy operator, and eventually we'll be talking about the Schrodinger's equation, and then we will introduce the potential term in the Schrodinger's equation. And that is when we will be knowing about the Hamiltonian of the function too. So thank you very much for watching. Subscribe for more.